In this video, we're going to take the two-dimensional Gauss quadrature method we learned in the previous video and apply it to the isoperimetric formulation that we learned in the last lecture. Let's refresh our memory about what we're talking about. In the last lecture, we discussed a generic quadrilateral element existing somewhere in XY space. And what we'd like to do is to find the local stiffness matrix K for this element. In order to do that, we need to solve this area integral, integrating over the area of this element existing in XY space. To do that, we first need to evaluate the result of multiplying the transform of the B matrix times the D matrix times the B matrix. This will result in an 8x8 matrix, which every member of that 8x8 matrix is a polynomial in terms of x and y. And we need to evaluate that two-dimensional polynomial. There will be 64 of them. And we need to evaluate the integral for each 64 members of that 8x8 matrix. That's difficult. Remember what we did with the isoperimetric formulation is we learned how to map this generic two-dimensional element to a standard two-dimensional element now existing in ST space, but now our element is a square going from -1 to 1 in S space in the S direction and -1 to 1 in the T direction. We still need to evaluate an integral which consists of these three matrices now times the Jacobian, or the determinant of the Jacobian, which remember is a polynomial itself in terms of S and T. We still need to integrate 64 times, once for each member of that 8x8 matrix, that 8x8 matrix formed by multiplying these three matrices together. But now I'm integrating from -1 to 1 and -1 to 1 in the perpendicular direction. We just learned how to do that. And notice that the Gauss quadrature method that we've learned in the previous two videos only works if we're integrating from a domain of -1 to 1. So the Gauss quadrature method is perfectly aligned with the isoperimetric formulation. We found to integrate or to come up with an approximation to this integral, all I need to do is evaluate these functions at 4 locations inside my domain and then sum up those evaluations together. So I can approximate this integral by this form. Here I've taken this double integral, I've rewritten it here. I've just made it a little bit more clear that the B matrix, the transform of the B matrix, and the determinant of my Jacobian are all functions of S and T. And every member of these various matrices will be a polynomial in terms of S and T. Evaluating this integral would be rather difficult for us as human beings. It would also be more difficult for a computer. But I can approximate this integral by simply summing, and note I'm have a summation symbol here, but I'm just going from j equals 1 to 2 and I equals 1 to 2. So this double summation simply means that 4 terms alone, and I'm evaluating at Si and Tj, but I and j only have 2 possible values, 1 and 2. So there's only 4 terms coming out of this summation. And remember, S1 and S2 are simply -1 over the square root of 3 and +1 over the square root of 3. And T1 and T2 are just -1 over the square root of 3 and +1 over the square root of 3. So evaluating this may seem somewhat tedious. But remember, you're not the one doing these function evaluations. What you're going to do is you're going to write a computer program that will do these evaluations for you and do the summation for you. It's fairly straightforward to write a computer algorithm to do this type of evaluation and summation, whereas writing a computer program to do this type of integration is very difficult. With this, we're pretty much done covering new material in this course. And it may seem like we've done a lot of work on paper. We've done a lot of work on paper to teach you the fundamentals and the theory behind finite element analysis. But finite element analysis is mostly done on computers. This wraps up lecture number 21. There will be one more lecture, lecture 22, where I will essentially summarize what we've discussed in this course and also talk a little bit about what comes after this course if you want to really use finite element analysis for a larger class of problems.